Hi, my name is Simon Hatch. Thank you for viewing this video. It is a short video. Hopefully it's going to be about 10 minutes long. So it's giving you an idea of the type of training courses that I would deliver. In the introduction, I explained the format of my training courses. The content is the same, whether it's face-to-face or via Skype. So in this sample presentation, each module always starts with the agenda, basically what I'm going to be covering in that particular module. So in this case, what I've done is taken a slide from my introduction module. It's a pretty fundamental question I start off with. And then each module I've gone through and pick a slide. So for instance, on the temperature module, I picked a slide about the history and giving you an idea of what the slide would be like. The last one is probably the most important point there of working smarter. All my modules are aimed at smart instrumentation and a continuous measurement. I don't focus on switches or pneumatics. I understand some people still use that, and it's what it does is great. But this is really talking about modern instrumentation and where the future lies. And this is really focusing on smart instrumentation and continuous measurement. The first fundamental question I ask is, why do you need instrumentation in the first place? So if I'm trying to explain to my friends what is instrumentation, I sort of compare it to what you have at home. You have your gas meter, your water meter. The simple thing is we do that, similar to that, but it's on an industrial scale. That's sort of true. But what I like to do is just compare it into your daily life. And you see the picture in front of you, it's a person and it's really highlighting the eyes. So the instrumentation, I will sort of say, is very similar to your senses, your sight, your taste, your smell, your hearing, etc. So if your sight is similar to your pressure, so for instance, I can read fine without any glasses. But if I'm looking any further away from reading a book, I need to wear glasses. So when I'm driving, it's pretty important for safety of me and other people that I'm wearing my glasses. I need to actually see what's going on, to react, to turn the wheel, to brake correctly, to make sure I arrive safely. So my sight is very similar to, for instance, my pressure measurement. So if I'm not measuring my pressure accurately, how do I know how to control it? How do I know to make sure it's safe? So it's really to improve the knowledge of the process, because fundamentally, yes, operations will know roughly or should know what the pressure is. However, when you put an instrument there, it's actually reading what's really happening. Sometimes, and it's always been the case, it's the instrument that's blamed. But most of the time, the actual instrument is reading correctly. It's just maybe not what operations expected or hoped the process variable to be. So it is improving the knowledge of the process. It's the integral part of your control system, a safety system that is in contact with the process. So you haven't got good data or intelligent information coming into your brain, you're not going to be able to make the right decisions. And that is what smart instrumentation is, and the benefits of it is. Each module, I started with a history. So I try to make my training courses as educational as possible. So it's not just reading a product manual and regurgitating what is in the manual. So this example is from the temperature module. Everyone knows the thermometer where you're using at home to measure your body temperature, whether you're getting a fever, whether your meter's fully cooked. But it came from Galileo. And a lot of these process variables, the history is from some academia, an academic, whether it's normally a physicist, but some theory they found. And then hundreds of years later, we're still using that theory in our case, an industrial situation to measure temperature using a thermometer, or as Galileo called it, a thermoscope. There are theories on all the modules about equations, and yes, I do have to cover equations, but I try not to make it too academic. There are books out there, you can do Google searches to find the detailed ones. But I wanted to try to make it as educational and people learn, not just from an industrial point of view, but they increase their knowledge. So yes, in the pH module, this slide comes from the pH, I explain what is an alkaline base and also what an acid is. But I also want to actually relate that into your daily life. So people can understand something like a lemon juice is an acid, fairly strong acid. Well, something like baking soda is a weakish alkaline. And in the middle there is some like blood or water. So you can compare if you're measuring pH, for instance, a wastewater treatment plant, or what a pH value of 2 relates to in your day-to-day life. And definitely for me, from a personal point of view, pH of 2 doesn't really make any sense. But I can sort of understand what the lemon juice is for a day-to-day life. Flow is probably the biggest module because there's so many different flow technologies out there, as well as products. It can be overwhelming to people because there is, and it's probably the same with most instruments, there is no perfect flow meter out there. But the first fundamental thing is you've got to understand what the process fluid is and what are the operating conditions in the first place. Because when you apply the technology, some technologies won't work, others will work, but maybe not as good as other technologies. As well as continuous measurement, I tend to focus on fluids because solids generally is a very specialized application. I can do training courses on solids, but generally I personally sort of say that are really different. Maybe you can sort of say slurries very close to solids, but I will still call a slurry a fluid. So the fluids are liquid slurries, gases or steam, and they are the fluids, the phases that I will focus on in my fundamentals of instrumentation. In the flow ones, as with all the technologies, I do about the principles of operation, where it came from, and explain in the Coriolis one of what is the Coriolis effect. But in this case, you can see a video in front of you that basically you've got a phase shift. What you do is measure the phase shift between this point, and the phase shift is directly proportional to mass flow. Other flow technologies talk about inferred measurement. Coriolis is direct mass measurement. Out of interest, I'll also explain about how density measured also using this effect. My training courses are designed and aimed at technology. They are vendor neutral. My view is if you want detailed product training, the manufacturers are very good and they got detailed documents, training courses on their particular products. But really you still need to understand the fundamentals, but also some good practice about installation. This slide I've taken from the pressure transmitter. So it's a differential pressure transmitter, measure the difference in pressures. So what you want to do is measure the difference in pressures between the high side and the low side. So you have generally isolation valves, which are normally for instrumentation purposes, needle valves. So because you've got a high and a low side, you've got 2 isolation valves. So they're 2 of your valves out of your 3 valve manifold. Third one is an equalizing valve. So when you install the pressure transmitter, which is on the right hand side there, you connect your high and low sides to the process. What you should be doing is zeroing the transmitter under flowing conditions. So what you would do is open up both isolation valves and the equalizing valve. So even if the pressures on the high and the low side is different, because you open the equalizing valve, the pressures at the pressure transmitter are the same. So hence you have a 0 dP under flowing conditions. And then you can zero the transmitter And then to put the transmitter in operation, you'll keep the isolation valve open and close the equalizing valve. When you close the equalizing valve, you will, if there's a DP, for instance, created across an orifice plate, you will have that same differential pressure being measured by the transmitter, having zeroed the transmitter beforehand, and eliminating any zero effects, which may be caused by insulation of not having that transmitter exactly horizontal, your impulse lines correctly aligned. So you always zero the transmitter before putting it into operation. The other installation is I'll go through radar and the level applications. The principle is obviously when you've got your radar gauge, what you want to do is your signal being reflected from the liquid level in the tank and then coming back to the device. However, in the tank, you might have other structures. You might have an agitator rotating round, and you could have your radar being reflected off this as well as the level in the tank. Now, yes, in the smart instruments, what you can do in the electronics is to mask these ghost reflections. However, a good installation, if you can maybe install that radar gauge a little bit further out, so your signal is less affected by these ones, you're improving your measurement of your level itself. That's what you want to do. And the last slide, the most important thing is, dumb device in the past is basically all it did is generate a process, an output for your process variable, normally a milliamp. Now that's fine. Your control system can operate off that. The safety system can work fine, and it's still the case. There's no real improvements as such. However, one of the benefits of smart instrumentation, the first thing is multi-variables. Most instruments now measure multiple process variables. A pressure transmitter can measure DP and static pressure. Coriolis can measure mass flow and density. However, if you only got one 4-20, how do you read those additional process variables? And that is where digital protocols come into. It can be fully digital, like foundation fill bus, probably bus PA, Modbus, or a hybrid, which is hard plus the 4-20. Both these signals now can be not just wired, but wireless. Wireless is something definitely will be becoming more and more in our industry. Maybe new applications you couldn't justify the cost of putting a wired device in. So you get these process variables coming into your control system. So from an operation point of view, you've got more data you can look at what's happening in your process. But the most important thing is also a maintenance point of view. So from a maintenance point of view, is normally operations will say maybe they've got the wrong process variable and it's the instrument that's faulty. So you go out into your field with either a handheld communicator, or now you can have a tablet with a Windows-based software on it based on FDT technology. But that's a reactive, so you're connecting, maybe just checking something's working fine. Well, potentially, every now and again, there is a problem with the smart instrumentation. However, the big advantage of unlocking the full capability of smart instrumentation is using an online device management system. So all your digital data, not just process variables, but diagnostic information, can be read online in real time. Then very easily, then your maintenance people can actually say, have I really got a problem with this device? Is it a fault? Is it something that's still working fine, but maybe it needs to be checked at the next shutdown, for instance? So diagnostics is a big, big thing. That really, if you've got an online device management system, you're unlocking not only just the additional process variables of smart instrumentation, but the full diagnostic capability of it. Thank you for your time, and I hope to hear from you and see you in the very near future.